Chapter 10 will deal with the inner products and scalar product. The inner products are a generalization of scalar products, and but in this lecture we start talking about inner products. Arguably, the most important structure a vector space can be possibly endowed with is the one of inner product. These structures are very helpful already for simple vector spaces as Rn. Simple meaning that the vectors are just n tuples of scalars. But they become fundamental for dealing with vector spaces whose elements are objects like functions. Let's give the formal definition, and from it we will see why these structures are so important. Definition: an inner product structure on a real vector space V is a function going from the cross product of V times V into R such that property number one is the symmetry. So if we multiply V1 with V2, we will get the same number as V2 multiplied with V1. Notice that this is called a product, but is not an inner structure of V, in the sense that if I take two vectors of V, I don't get a vector of V back. It's called inner, but still is not an inner structure of V. Notice that we get just a number back, not a vector. So it commutes in a sense if we see this as a product, but this property is called symmetry. And then we have two properties combined together in this expression, which involve linearity. You remember homomorphisms that we covered in the chapter 9, and in that case the argument of a homomorphism, the domain, was just a vector space V. If we have two vector spaces and we take the cross product and we have a function from the cross product of V times V, we can talk about multilinearity, in this particular case bilinearity, because we have two arguments, and so we can actually require this function to be linear in the first argument, first variable, and in the second variable. So by symmetry we can just phrase this as linearity in the first variable, that automatically it will hold also for the second variable. This property reads as follows: if we take a linear combination of two vectors, v1 and v2, with coefficients alpha and beta, and we multiply by vector w, what we will get is that this vector distributes to the individual summands, and the scalars just passes through the sign of product. So this is the same as taking the linear combination of the inner product of v1 with w and v2 with w with the coefficients alpha and beta. So this is linearity with respect to the first argument, using the same kind of notion that we introduced in chapter 9. And then the third property is that we require that when we take the inner product of a vector by itself, we will always be getting a number that is strictly greater than 0, and as we will see, except for the case in which V is 0 itself, is the 0 vector. So the requirement is that to be greater than 0 for all the non-zero vectors, and this property is called the vector, the inner product being a positive definite. Remark: if we take the inner product of 0 with itself, we will be getting the number 0. And this is the only one for which this property holds. This is the only vector for which we have that the scalar, the inner product of the vector by itself is the number 0. And this follows by linearity. For example, if we write, so the property number 2, if we write 0 as 0 times v for any vector v, little v in the vector space v, then the inner product of 0 by itself is the same as writing 0, inner product of 0 times v, comma 0 times v. But as we have seen, 0 just passes through the sign of product, so this is equal to multiplying 0 times the remaining inner product, but 0 times any number is 0, so we have proven this equality. The property of bilinearity of the inner product implies that all the information contained in the product can be derived by finitely many numbers. Let's see how. Fix a basis of v and call it vh for h that goes from 1 to n, and w and z two vectors of v. Therefore, they can be expressed uniquely with a linear by a linear combination of the basis vectors vi's, summation for I that goes from 1 to n with alpha I times vi, and this expresses w, and the same for z. We have a unique linear combination of the vectors vj with coefficients beta j. Let's multiply w by z with this inner product and see what happens if we apply the multilinear properties that we have just required the inner product to have. We have two linear combinations in the first factor and the second factor. And then we apply the property number 2 for the sums, where we could apply all at once, but let's just split it in two steps. First, we apply the bilinearity of the first argument and second argument with respect of the sums. So the sums go out, and what remains are two sums of these kind of products, vi multiplied by alpha I and as a vector times a scalar, and all these becomes a factor inside the inner product, and the other factor is beta j times vj. Now we apply bilinearity with respect to multiplication by scalars, so both alpha I and beta j go out from the inner product notation, and what we finally get is this double sum, one over the index I, the other over the index j, of these summands. Each summand is alpha I times beta j. This product is a scalar that multiplies this other scalar, that is the inner product of vi times vj. Therefore, the inner product of two randomly chosen vectors of v, namely w and z, can be uniquely expressed as a sum of these inner products of the elements of the basis for any I and any j. Hence, the n squared numbers, inner product of vi times vj for I and j that go from 1 to n, univocally determine the inner product on any pair of vectors. So once I know these n squared numbers, I know the inner product of any other two vectors, as long as I can express these vectors in functions of the bases that I've chosen, of which I know the inner products of. Remark, let V equals to Rn, And let's write his elements as column vectors. Remark A, define A to be the matrix Aij, with Aij is the scalar given by the inner product of Vi times Vj. Then we can recover the action of the inner product by means of the matrix A. So we have n squared scalars, and since they depend on two indices, it is natural to ask ourselves if arranging them in a matrix, we can actually use the algebraic structure of matrices in order to recover some information about the inner product. And the answer is yes. Indeed, we can write explicitly the expression of W times Z in this form. We take the vector W, which is a column vector, we transpose it, becomes a row vector, and we multiply on the right by the matrix A, and then again on the right by the column vector Z. And this equals the inner product of W times Z. One can just write these introduced coordinates for W and Z in function of the canonical basis, so writing them as just a row vector and column vector, expand it, and see that you can recover exactly the same expression as we wrote before. Notice that because of property 1 of the symmetry of the inner products, A is a symmetric matrix. Simply because if we invert I with J, we are multiplying instead of Vi times Vj, we are multiplying Vj times Vi, and by the symmetry, these two numbers are the same. Vice versa, if B is any symmetric matrix, the function that associates to the pair vectors W and Z in V, the number that we have written here, this defines an inner product on V. Okay, so for Rn, we have a correspondence between symmetric matrices and inner products of inner products on Rn. We introduce now a few notations. First of all, the norm of a vector V is the number indicated with two vertical bars and the vector inside, and is defined to be the square root of the inner product of V times itself. We require this to be a strictly positive number if V is different from 0, or we have shown that this is 0 in the case V equals to the 0 vector. Now notice that the norm depends on the inner product. So if I change the inner product, the norm of V changes. If I take a particular kind of inner product, we will see later, which is called kind of Euclidean inner product, this gives exactly the Euclidean distance of this vector from the origin. But for other choices of inner products, this is no longer true. It doesn't give the Euclidean distance. It can give a distance according to this inner product. So this one can show that any inner product induces a distance, an associated distance. In fact, any inner product associates a norm, and then from the norm we can define the distance. So there are these two intermediate steps going from the inner product to the distance. From the bilinearity of the inner product, we immediately see that this norm is in a sense linear, because if you multiply V by lambda, this lambda comes out of the sign of the norm, the notation of norm, but with an absolute value. And this holds for any scalar lambda and vector V. Next definition, we call two vectors v and w orthogonal or perpendicular if the inner product of one with the other is 0. And again, the concept of orthogonality depends on inner product. We have a native one, which is, in the case of v and w, are vectors of R2, for example. It is the usual notion of orthogonality, meaning that they have an angle of 90 degrees, one with the other. But again, this corresponds to a very special inner product, as we will see, the Euclidean inner product. But for other inner products, we may have that two vectors are perpendicular, orthogonal, even if their angle between them is not 90 degrees. Let's now say a few words about the relevance of inner products, as I have anticipated at the beginning of the lecture. Let V be an n-dimensional vector space endowed by an inner product. Then there always exists a basis EI such that the inner product of EI times EJ is 0 if I is different from J, but it is 1 if I equals to J. Well, in that case, we have the following fundamental fact. For each W in V, W can be uniquely expressed as a linear combination of this basis AI, the basis that we have just described having this very special property, and the coefficient of this linear combination is every coefficient is computed by means of the inner product. We just have to take the vector W itself and multiply it by each of the basis vector alternatively. So if the vector here is EI, we will be multiplying W times EI. In other words, the inner product and the basis EI provide a way of finding coefficients of the linear combination expressed in any vector in function of the EIs. When vectors are n-tuple of scalars, that means that V is the n-dimensional, for example, n-dimensional Euclidean space where n is any positive integer, we can find coefficients of linear combination by solving systems of linear equations. This is how we did so far in this course. This is a vector, and as an element of Rn, it is an n-tuple of scalars. These are also n-tuple of scalars, and this equation between this vector and this vector, each of these multiplied by a scalar, can be solved by solving a system of linear equations. One equation for each coefficient of these two vectors. In general, though, we cannot assume that W and EIs are n-tuple of scalars. They can be much more exotical elements of a set. For example, they can be functions. So in that case, solving this system, this equation, having an exotic object here and an exotic object here, can be extremely complicated. However, if we have an inner product on our vector space, we can solve much more easily the problem by means of this equality that we have written here. However, when vectors are other objects, the problem of finding linear combinations, or even more generally series representing vectors in function of a basis, is a non-trivial task. In this context, the fact just stated is crucially important.